Hello class. So this afternoon I'm going to be talking about continuations. So continuations are an extremely powerful control flow concept. They're really mind-bending. So throughout this video you're really going to have to pull up a Dr. Racket interpreter and play around with the examples. If you just watch the examples, I promise you're not going to be able to understand them. And as you're working through these, I need you to pause the video and go through them 3 or 4 times just to make sure you have everything rock solid. Because otherwise, these are pretty challenging things to understand quite genuinely, but once you figure them out, they really kind of make sense. But it's easy to misunderstand them. And I think the thing that's really exciting to me about them is that there are a lot of different constructs in programming languages that you probably haven't really thought about before that codify what's called the control aspect of the program. So what do we mean by control? Well, control means how the program executes in terms of what statement gets executed next, right? So we often think about programs as you execute one statement and then you execute the next statement, you call a function, so you go to the first line of that function, you return from a function, so then you go to the point where that function was called, right? So that's kind of normal execution. But we also have other kinds of constructs like loops, right? Loops go, when you hit the end of a loop, you go back to the beginning of a loop. We also have constructs like exceptions, right? When you throw an exception, you might exit outside of the function where you threw that exception. You're going to exit back up to the exception handler. All right, so continuations are going to allow us to codify all of that, right? So if you kind of wonder, well, why are we learning about this continuation stuff? It's because you really absolutely will face places in your sort of day-to-day programming life like exceptions and like loops and other kinds of things. And all of those are instances of a general construct called a continuation. All right, so a continuation precisely is a return point, a call stack, or the remainder of the program, but viewed as a function. So we can think about a point in the program being viewed as a particular function. All right? And that's something that's really exciting. It's going to give us an extreme amount of power. And it's going to be able to allow us to essentially jump around execution in the program by calling functions. All right? So in Scheme, continuations are actually first-class values that can be captured by using a special function, a really special function named callCC. And then we can invoke those functions later. All right, so I'm going to talk a little bit about what continuations are at a high level. But to be honest, my guess is that the first time you hear this really will not make sense to you. It really is a pretty complicated concept. And so what you're going to have to do is you're going to have to go through this video, you're going to have to work through the examples, and you're going to have to come back and watch it again. So I think once you work through the examples, when you see this material a second time, you'll be kind of more primed to understand the whole story. And I really hope you take the time to do that. All right, so we can think of a first-class continuation in several different ways. We can think of a continuation as a value encoding a saved return point to resume the execution. So we can think of a continuation as some point that if you call some function, it's going to go back to that point or jump back to that point. The ability to jump back to somewhere in the program. Most of the time when we call a function, we don't think about going back to a particular point in time. Continuations are going to allow us to do that. Similarly, a continuation can be thought of as a function that encodes the rest of the program. We'll see what that means in a few seconds. A continuation is a function that never really returns. So what I mean by that is that all calls to continuations are tail calls. You never call a continuation and then come back to it, at least with the kinds of continuations we'll see. There are other kinds of continuations out there, so in this class we're only going to talk about undelimited continuations, but there are also delimited continuations. There are a few different ways to teach this stuff. I find that different students understand different things. In particular, it might be helpful to learn about delimited continuations first, but this is the way that I'm going to teach it this semester. And so I probably, well, if you're interested in learning about the other kinds of continuations, feel free to reach out and chat because I don't really think there's one particular way to present this that works best for everyone. So you've probably used a lot of kinds of control constructs before, but haven't sort of realized that they're continuations. So in particular, a goto is a kind of continuation. So is a loop. So different types of loops. There are a bunch of different types of loops. There are while loops, do while loops, for loops, all these different kinds of things. There are return statements. So when you make a return from a function, you go back to the calling function. That is a transfer of control. What do I mean by control? Control basically means where is the program currently executing? What is the current control point, right? The control point of the program is the point that is currently being executed, right? Exceptions are a really good example of kinds of continuations, right? When you throw an exception, you go to the proximate exception handler. And then if you've been a C programmer, you've probably heard about a function named long jump, which allows you to sort of jump across routines in a way that doesn't, sort of kind of breaks the stack. And then you also may have heard of cooperative concurrency. So if you've seen traditional threading models, these are not so much continuations, but if you've seen things like coroutines, for example, the Go programming language has these things named Go routines that allow really kinds of nice concurrency primitives. All of those things can also be thought of as continuations. So even though these things look really confusing at first, they are actually the primitive form that generalizes all of these different kinds of control constructs. So, if exceptions seem confusing to you, the reason that they're confusing to you is that they're instances of control operators. And if you can understand how continuations work, you'll have a lot better ability to conceptualize how exception handlers work. So this really is something that I think is worth learning about. I think that there are some things in the class that are less obviously useful for your day-to-day life, like for example lambda calculi and things like that. Even though I think those things are still useful once you sort of have the perspective to appreciate them. But I think continuations are one of these things that, even though they're kind of tricky, they are extremely practically useful for being able to write code in your day-to-day life. And in some ways, some people have said that continuations are said kind of to permit time travel, in the sense that they permit jumping back to a staved dynamic part of the stack. So a continuation is, in some sense, sort of a snapshot of the stack, so that you can jump back to it at some point in the time. And this can either shorten the stack, or it can grow the stack, or it can replace the stack entirely by an entirely new stack. All right, so the form callCC is going to expect a function that takes a single argument, and that argument is going to be the continuation. All right, in particular, the current continuation. All right, so let's look at an example of this. All right, so let's take this piece of code right here, and let's put this in Dr. Racket. All right, so we've got 1 plus, and then we've got callCC, and then lambda k, and then we're invoking k on 2. All right? So what is this going to do? So let's run this in the debugger, and we're going to run it step by step. So what I'm going to do is I'm going to put a pause right here. So we're going to hit go. Okay, and we've got, now we're at this point where we're going to do 1 plus and then this call to callCC. So we evaluated 1 atomically. We didn't have to do anything to do that because 1 is already a primitive operator. And now we're going to do callCC. Now callCC is going to, and this is very crucial, callCC is going to save a return point. It's going to save a return point at this point right here. And that return point is going to get bound to k. So k, if you call k immediately, you're going to jump back right here in the code to the point where this thing, the whole context colored in gray right here, that whole context is going to be the thing you're going to jump back to. You can sort of think of this whole gray thing as a hole. And that hole is going to be plugged with whatever value you give as the argument to k. So when I do a call CC, it's going to bind k, and then it's going to execute the body of this lambda. And then when I call that k, suddenly I'm going to jump back to where I saved that return point of that call CC. So what was the value? Well, we have to look at what's inside this hole. So let's say that I take this entire hole right here, and I wipe all of this stuff out, and I replaced it by just the value 2, which is the argument that I'm giving to call CC. Well then, how would the program continue? Well, it would be plus 1, 2, and then that would continue to 3. So that's exactly what's going to happen. Call CC, again, to reiterate, because this is actually confusing, and you have to hear this a few times. Call CC is going to save a return point and bind that return point to k. When that return point is invoked, you will jump back to that return point. You will not do anything else within this execution. You will go back to that return point, you will fill in that hole, and then you will continue the execution. So let's see what happens when we call k. Boom. We're going to return, we're going to do that plus, we're going to print 3, and now we're done. All right? So this call CC, it's going to take the stack at the second argument expression, and it's going to save it as a function. That function is going to be bound to k. When that value k is invoked on a value at some later point in time, execution is going to jump back to the point at which that continuation was saved, i.e., when that call CC was taken. And then that entire place where the call CC sits is going to be replaced, that entire hole of computation is going to be replaced by whatever argument is given to that function k. Right? So you can also similarly think of it. So what's the argument? Let's look right here. Pop out of the debugging mode. Okay, so if I take my call CC form, think about putting a hole right here. When I invoke k, this hole will get filled with whatever that argument is. So let's say that argument is 23. Well then, that hole is going to be filled by 23. And then 1 plus 23 is going to give us 24. What about if it is plus 23, 1? Well, what's going to happen? Well, k is a function. So before the function k gets invoked, i.e., and remember, invoking k zooms us back to this point right here and fills in that hole. Before k gets called, because it's still a function, its arguments get evaluated. So this 23 plus 1 will happen. And then we're going to take that value 24 and replace the hole right here, and then do 1 plus 24. So let's see what happens here. And then of course, okay, so we get 24 right here. 1 plus 24 is 25. All right. So let's go back to the slides. Now, also crucially, let's point out something here. Let's say that I have, if I have a lambda right here, this lambda, let's say it does two things. First, it does k of, let's just replace it with 24. And then I'm going to do display ln hello world. Now, first of all, you need to remember what happens when a normal lambda executes. So for a few seconds, let's just remember what had happened under a normal condition. So let's do lambda x, and then we'll just comment this form out for a second. Okay, so what's going to happen? So I'm going to bind this to k. I'm going to call k on 24. That's just the identity function. So I produce this value just returns 24, gets computed because it's lambda x applied to 24. So that gets computed, and then after it gets computed, lambda just executes a whole bunch of statements in a row. So this gets computed, and then I go to display ln, hello world, and then now this function is done, and then the whole program is done. All right, so if I put a few different statements after a lambda, a few of them will happen in a row. So I compute this, I drop it on the ground, and then I go and continue to compute this. Now let's say that I take a continuation instead. Something different is going to happen. And it's very important that this is different. So you really should be checked in right now. You really should be working at your computer, working on these examples and making sure you understand the differences between these two, because this is the really crucial part. All right, so let's see what's going to happen. I'm going to uncomment this region. Now, this first one displays hello world. What about this second one? 25 gets computed. All right, display hello world. None of that ever happens. This code gets skipped. Now, why does that happen? Well, let's think back to what's going to happen. We're going to do +1, and then we're going to take this continuation and bind it to k, meaning we're going to take this little hole right here. We're essentially going to take this piece of code. K is essentially lambda x, and then we can fill in the hole, +1x, right? Because if I think about, this is the control point that if I invoke k, it's going to zoom back right to this point, and then it's going to drop the rest of the computation. So it's going to zoom back to that point and finish the program. So that's exactly what's going to happen here. I'm going to do +1, and then I'm going to do call cc. I'm going to bind this continuation to k, and then I'm going to call k of 24. I'm going to jump back to this point, replace this entire thing with just 24, and then do 1 + 24. And remember, a call to a continuation never returns. They are always tail calls. A call to a continuation never returns. You will skip the rest of the code past the continuation. So if I call k, you might think to yourself, okay, well, you call k, then you go here. No, that's not what happens. Once you invoke k, now you've jumped back to this point of code. This continuation is now done. And then you call 1 + 24. So the rest of this stuff gets skipped right here. And this is extremely important. If you do not understand this, you should be asking questions about it right now, because this is the one thing that if you don't get, the rest of the lecture is not going to make sense to you. All right? So if you're at this point, if you're watching this and you don't get what's going on, you should be asking questions in Slack. We should be making sure you get it so you can understand the rest of the video. All right? So this call CC right here, it binds a continuation. You invoke that continuation. You go back up, throw the rest of this context away because that's where the call CC was taken, and then you execute that with 24, and then nothing happens here. Right? Okay. And then we call these undelimited continuations because our continuations are just going to continue on the rest of the program. All right? So let's look at another example. We've got 1 plus. This is essentially similar to the last one, but I think it's worth pointing out because these are pretty crucial examples. So we do 1 plus, call cc, lambda k, print 0, k2, print 0. Once we invoke k, remember, when you invoke a continuation, it's really a jump. It's not like a normal function call. A normal function call would call a function and then return and then continue to go on to print. This invocation of a continuation is really a jump. Just like you can think if in a programming language like C, usually have something like you'd have a label and it would say something like go to and then some label. It's like that. Because once you have a goto, you never return, right? A goto tells you to jump to some other piece of code, right? Well, it's the same thing. Continuations are just like gotos. And for that reason, you probably don't want to use callcc all that often. In fact, liberal usage of callcc is not really a good thing. It's a pretty powerful control construct. It's kind of an ugly control construct, even though it's a functional programming sort of, it's basically a functional goto. You really want to use some of the idioms that I'll demonstrate. So I very rarely use callcc in the kind of code that I write on a day-to-day basis. But I write a lot of code that is derived from callcc. All right, so if I use callcc, usually I wrap it in something like a macro, or I write some functions that sort of wrap around it, because I don't want to like mix callcc in with my typical code. It's a pretty high. It's something that if it's in your code, you really have to think about what's going on quite a bit. All right, so it's a very powerful control flow construct, but you have to be very thoughtful about how you use it, because it can really, jumping around the program in just kind of arbitrary ways is really confusing, and is a bit of power that you have to be really careful when you use. All right? Okay, so we're going to see a whole bunch of more examples. So we can think of something like, if we look at this, callcc's behavior is roughly the same as the application of, when I take it right here, I can think about taking this entire computation right here and thinking about, well, what's going to happen? Let's say I just copy this. If I think about where the callcc is, I can think about turning that into a whole. So I can think about, once the callcc is captured right here, what is the rest of the program going to do? Well, that's going to be like a whole. And I can think about that functionally as lambda x. The font's going to be inconsistent. That's too bad. There we go. Lambda x, and then plus 1 x. And that's really the function that k is going to get bound to. And in fact, really, it's going to be more like in Racket, when I only have one function and I actually invoke that function, well, it's going to do a little bit more. It's really actually going to print that out to the screen. So it's going to print out, and then it's going to exit. All right, so I can really think of k as being bound to this. So when I get here, k is really bound to a function that takes x. Oops, I put x in the wrong place. There we go. And I think the parentheses balance out, but it's the one here. So I can really think of it as being roughly the same as this application right here. All right, well then, once I bind to k, this is what I'm binding. This thing that takes a number in and then does exit print of 1 plus n. All right? Where the highlight continuation right here, the thing being highlighted, takes a return value for the callcc expression and kind of finishes the program or continues the program. That's why they're called continuations, is because they give us a recipe for how to continue the program. All right? So let's work through a few different examples. So I'm going to work through this first one here, and then I'd like you to work through the next two, but I'll also explain them. So let's look at this example right here. Paste this into Dr. Racket. Okay, so we've got a callcc at this top level. So we know that our first continuation is going to replace this entire thing. So if I invoke k0, I'm going to return right here, which is just the end of the program. So if I invoke k0, I just go to the end of the program and put in the return value that I would get. So like, let's say I call k0 on 3, well then I just go to 3. Okay? So I call cc with k0. So then I execute that one. I haven't called k0 yet, so then I do +1, and now I take a second callcc. And this is a callcc that's going to go to this point right here. All right, so if I were to go to this point right here, if I invoked K1, I would return right back here. All right, so then so I still haven't called any of the continuations yet, but then finally I get down, execute through here, and then I go to +1, and then K0, okay, boom. So now I jump back right here. All right, I don't do anything after this K0. I don't go to +1. I don't go to then go through this +1, but instead I just go and jump immediately back up to the top level, because remember, continuations never return. They're always tail calls, and they are always transfers of control to the point where that call CC was taken. All right, so the answer to this one is just 3, because I jump back up right here and return the answer 3. All right, so that's the first one. Why don't you try to work out the next two yourself? Why don't you pause the video right here and see if you can figure out what the next two are, and then I'll explain them. All right, so let's look at the next one. So I've got call CC K0, I've got call CC K1, and then I do +1, K0, K1, 3. Okay, so I'm going to call this K0. To call that K0, first I have to compute K1. Okay, so then, boom, I jump to this point right here. I replace this entire thing with 3, and then I just get +1, 3, and then the rest of the thing executes normally, right? Because after I call this K1, I never come back. I don't go and actually call K0. Even though it's syntactically right here, because I invoke K1, I'm going to jump back up to this point right here where that K1 was taken. All right, so I'm going to put the 3 right there, then I execute normally. And then I should also say, let's say I take a call CC on this K0, but then I never use K0. Well, that's essentially just like a no-op, right? I'm not doing anything with it. I'm saving the continuation for later, but I'm never actually invoking that continuation. All right, so that just kind of executes normally. All right. What about this last one? All right, clear ourselves some space. Okay, so now I'm going to do +1, and then I'm going to do call CC on this right here, jump back up to where that K1 was taken, and then I'm going to do K0 on 1 right here. So then I'm going to do to compute this thing right here. That's just going to be 3, because right in here I'm going to invoke on K1. I'm going to jump back up and replace this with 3. And then K0, 1, well, that means that I abort the, I was going to, after I finished K1, if this had just been something like lambda x x 1, that would have ended up computing 1 and done the addition, but it's not that. It's a call to this K0, which means I actually jump back out here and then replace the entire thing with 1. Okay, so that one's 1. All right, so those are the answers there. All right, so those are a few examples. I really encourage you to go through those and make sure you actually understand how all of those work. Those are things that absolutely will pop up on the final exam, and you really should be able to understand those. All right, so they're sort of bedrock material to understanding continuations. And now here's an example of where continuations get a little bit tricky, because this is when we're going to start using continuations to actually implement control constructs like loops and things like that. So a pretty common idiom for using call CC is to let bind the current continuation. All right, and we can actually use this to make loops. So let's take this piece of code here. Open up Dr. Racket. So first of all, I want to say, let's say I have some code, my code here, something like that. So let's say I have this bit of code right here. Well, let's look at this point here. If I take a call CC right here, well, if I were to invoke this K within this block, it would plug this hole right here, bind CC, and then execute whatever was right here. All right? That's a tricky enough concept. We really need to go over it again. So let's say that I do this call CC here. It binds K. Well, the current continuation is going to fill in whatever I'm going to get right here, and then bind CC, and then use it right here. But here is the crucial trick. If I call CC on the identity function right here, then what I'm doing is I'm binding this return point essentially to itself. All right? That should remind you of something. It should remind you of the U combinator, which is sort of making a copy of yourself. Right? So I'm binding this return point into CC so that if I invoke CC anywhere in this body, I'm going to zoom back up right to here, bind CC to itself again, and go through that body again, which will essentially give me a little infinite loop. All right? And note that applying call CC on the identity function is exactly the same as applying it on the U combinator. All right? So if I take this piece of code right here, I replace this right here, well, if I invoke K right here, it's going to go back up, bind CC to itself, and go run this code right here. But if I invoke K on itself, I'm saying go right here and bind CC and do the rest on a function that if I call it, I will bind CC and do the rest. All right? That's one that you really need to think through, and I really would encourage you strongly to talk about in your discussion groups and really see if you can figure this one out. It is pretty tricky. All right? So let's see how we can actually use this in some examples, and I think it'll make a little bit more sense. So I can use this to create a little loop, something like a do-while loop. So we're going to use a feature of Racket that I told you never to use, but it's going to be helpful because call CC is going to break the stack in ways that are not going to allow us to easily access variables. So for one time, I'm going to use something that I've told you not to use in the past, which is setbang. So let's define x as 0. And then let's say setbang x to x plus 1. And now, if x is less than 10, call CC on itself, otherwise return x. Let's see what this code returns. It returns 10. So let's make this in fact a little bit easier because I only want to explain one iteration of the loop. So what's going to happen? Well, first we bind CC to a function that goes, if I invoke it on itself, I can continue the loop. So CC is going to be bound to a function that will accept a function and will continue on, and if I setbang, the first time I go through this, I'll setbang x to x plus 1. I'll say if x is less than 2, which it is because the first time it'll be 1, it'll invoke CC on itself. So then I'm going to jump back right up to here and then bind CC again to itself, because remember, the argument that I pass to CC will get put in for this value right here. So I'll be replacing that with CC, which will allow me to continue the loop. Now that's a very important thing. If you haven't understood this yet, go back in the video and think about, why do I need to put CC right here? Why not the value 5? Right? Well, if I did that, then I would be binding 5 the next time I would be going through the loop. right? Instead, I want to make sure I put in that value CC, which will allow me to continue the loop. And this is the same exact thing, essentially, as the U combinator, but using continuations. It really is mind-bending. It's a really cool piece of technology, but it's also a very powerful and a fairly complicated piece of technology, which is why we don't use it often, all right? And then we're saying otherwise, just return X, all right? And that's going to give me my exit value. So that's how I can encode a loop, all right? Another case that I can use it is what's called a preemptive return. So if you've ever seen, if you've programmed in probably a normal programming language, the kind of programming language you wish you were programming in rather than Racket, you're used to this keyword named return. And what return means is just jump out of the function. Don't execute the rest of the function, just jump out of it. Well, you can easily use continuations to wrap the entire function in a call CC with this function return, and then if you invoke return anywhere in that function, it will just replace everything in that function with whatever that return value is. So let's say you call return X right here. Well, that will just jump up to here and return X, and then that will be the return value of the function. All right? Otherwise, if you don't, it'll just keep doing and return normally. All right? So call CC. Call CC makes a tail call. You can see this return point. It's the same as that one. Sorry, this slide actually goes with the U combinator stuff, so I'm going to move that around. All right. And we can also use this for implementing continue and break. So a Python while loop that supports continue and break can also be implemented using call CC. All right, so you probably have seen in Python, if you have something like continue, that means exit the rest of this iteration of the loop, just go back up to the top of the loop again, restart it. You can do the same thing using continue and break. Now, I've talked quite a bit about this so far today, and I think we've covered quite a bit of material. So I'm probably going to leave it right here and let you just work through these examples and discuss them in Tuesday's groups. And then we'll pick this material back up on Thursday. All right? So thanks.